Hi everyone. So in this video, I'm going to be going over the most requested questions from the final exam review. So first off, we have number 1b. So number 1 was just asking you to evaluate a whole bunch of integrals. And if you look at what the question says on number 1, it also mentions that some of the integrals may be improper. And so if you reach an improper integral, you have to make sure that you're either evaluating it using limits or possibly using the comparison test to determine whether it converges or diverges. So this one, when you first look at it, it may not appear to be an improper integral, but it actually is. So why is this an improper integral? Well, remember that any integrand that is undefined at a particular x value, and we'll see that this one does have certain x values that would make the integrand undefined. If the integrand is undefined at an x value, and if that x value falls between the bounds or is one of the bounds, then that means that the integral is improper. And so looking at this denominator here, because the denominator cannot be 0, we know that this denominator is undefined at two different x values, right? It's undefined when x is -1 and also when x is +1. The -1 doesn't matter to us, but the +1 does. So it's undefined at x is equal to 1, and that's an issue because 1 falls between 0 and 2, right? So this tells us that this is an improper integral. And so because it's an improper integral, that means that we need to use limits to evaluate it. But before we can jump into the limits, we first need to split this up, right? Because if you think about how have we dealt with limits with improper integrals, we always do that when the undefined value or the infinite value is one of the bounds. And so if it's not yet one of the bounds, we need to make it one of the bounds. And the way we do that is by splitting this up. So we're going to split this up into the integral from 0 to 1 of x over x squared minus 1 dx plus the integral from 1 to 2 of x over x squared minus 1 dx. And now we can rewrite this using limits. So this is going to be the limit as t approaches 1 from the left of the integral from 0 to t of x over x squared minus 1. And then we have, again, the limit as t approaches 1, this time from the right, of the integral from t to 2 of x over x squared minus 1. And so now really we just want to focus on evaluating one of these to start. And then if one of them converges, then we still need to try the other one. But if the one that we do first diverges, then we're done. Then the whole thing diverges and we don't need to do any more work. So let's start with the one on the left. So we want to start, we don't want to forget about the limit, but really when you're evaluating the limit of this integral, the first thing you want to do is evaluate the integral. So let's start by just focusing on the integral. Now, looking at this integral, we're going to want to do substitution, right? So if you were just asked to evaluate, I'm just going to take the bounds off for a moment because usually when you're doing improper integrals, if you're going to do a substitution, it's easier to not change the bounds because sometimes when you change the bounds, you kind of make the limit a little bit more complicated. So generally speaking, I would recommend if you see that the integral within your improper integral is something where you would want to use substitution, I would recommend that you make it an indefinite integral, find the antiderivative, and then put that back in. So just kind of focusing right now on evaluating this as an improper integral. Okay, so why do I say we want to use substitution here? Well, notice that the denominator is x squared minus 1. The derivative of the denominator is pretty similar to the numerator, right? The derivative of x squared minus 1 is 2x. That's close enough to x that we can make this work. And so our substitution is going to be u is equal to x squared minus 1, and then du would be equal to 2x dx. And so that's going to make our integral now the integral of x over u times, so if du is 2x dx, then that would mean that dx would be du over 2x. And so we can put in du over 2x. We can cancel out these x's. And so we're left with 1/2 times the integral of 1 over u du. So what is the antiderivative of 1 over u? Well, we know that that is ln of absolute value of u. So we have 1/2 times ln of absolute value of u. I'm going to write plus c. We're not going to use that later, but I'll write that there for now. And then we can go ahead and put the u value back in, right? So we have 1/2 times ln of absolute value of x squared minus 1 plus c. Okay, so now that we have our antiderivative, now we can go ahead and put that back into our integral, right? So we were evaluating this integral from 0 to t, and so now we can jump ahead and say, okay, this is going to be equal to our antiderivative. So let me give a little more space here. So 1/2 times ln of absolute value of x squared minus 1 evaluated at, so what were the bounds again? They were t and 0. And we're taking the limit as t approaches 1 from the left. So now let's go ahead and put in our bounds. So we're going to get the limit as t approaches 1 from the left of 1/2 times ln of absolute value of t squared minus 1. And then from this, we're going to subtract, actually, well, I'll put the 1/2 both times. I could have factored it out, but I'll just leave it here. So 1/2 times ln of absolute value of 0 squared minus 1. So that's ln of absolute value of negative 1. So just plugging in the bounds. And so now we can continue to see what we can simplify here. So we have the limit as t approaches 1 from the left of 1/2 times ln of absolute value of t squared minus 1. And then over here we have minus ln of absolute value of negative 1. That's the same thing as 1/2 times ln of 1. And then ln of 1, that's 0, right? So ln of 1 is asking what power you have to raise e to get 1, and the answer is 0. So this whole term just drops away. And so what we're left with is just the limit as t approaches 1 from the left of 1/2 of, oops, my pen just stopped working, 1/2 times ln of absolute value of t squared minus 1. Okay, so now we can think about what is this limit? You know, what is going on with this limit? So what does it mean to take the limit as t approaches 1 from the left? That would mean that you're plugging in numbers that are just below 1. So numbers like 0.9, 0.99, 0.999. So if you're ever stuck evaluating a limit like this, one way that you can figure out what the result of that limit is just by testing out numbers. So you could go into your calculator and plug in, 0.9 squared minus 1, take ln of absolute value of that, multiply it by 1/2, see what the answer is, and kind of see where your answers are trending. So plug in 0.9, plug in 0.99, 0.999, see, like, are those numbers kind of flattening out towards a certain value, or are they going down to negative infinity, up to positive infinity? And in this case, it's going to be going down towards negative infinity. And so the reason I know that without plugging the numbers in is basically if you're plugging in numbers that are very close to 1, then you're going to be getting things that are close to taking ln of 0. And ln of 0 is undefined because if you think about what the graph of ln looks like, it looks like this. So as you're plugging in values that are closer to 0, ln goes down and down and down towards negative infinity. And so the result of this limit is negative infinity. And so we can conclude that this integral diverges. So again, I think there are functions that it's nice to be familiar with, to be aware of the fact that as x approaches 0, ln of x goes to negative infinity. But if you don't have all of those kind of memorized or you're not familiar with all of those, you can always test out numbers. And you're just looking for, as you plug in numbers that are getting closer and closer to the place you're taking the limit of, where are the results heading towards? And you should see if you plug in numbers like 0.9, 0.99, 0.999, that you're going to get these smaller and smaller negative results, which tells you that it's trending towards negative infinity. Again, just to reiterate, you do not need to then go and do this part. And if you were to do this part, and let's say you got positive infinity, you could not then add those together and say negative plus positive infinity is 0. You just say it diverges as soon as you get any kind of an infinite result. Okay, so next up we have number 1j. So on a similar note to the last one, this is another improper integral. And this one is more obviously improper, right? Because we see that one of the bounds is infinity. Now on the test, I think the way that I phrase things, it should be pretty clear when you're expected to use the comparison theorem versus actually evaluating. So remember that with the comparison theorem, you cannot say like if the integral converges, the comparison theorem does not tell you to what value it converges. It can only tell you whether something converges or diverges. So why am I talking about the comparison theorem? Well, basically, we don't have any good way to evaluate this. If you tried to go and evaluate this integral, we just don't have the tools that we would need to figure out what the antiderivative of 1 over x minus e to the negative x is. I mean, you could try, but it's just a little bit too complicated. Nothing really works out in terms of the methods that we've been learning so far. And so that's why I'm thinking that we should use the comparison theorem. As I mentioned on the test, I think it will be a lot clearer when I expect you to use the comparison theorem versus actually evaluating it. But yeah, here we're going to use the comparison theorem. Okay, so what does the comparison theorem say? Basically, it says if you can find a similar integral to the one that you're looking at here, which you are already aware of whether it converges or diverges, if you can then show that this function that we're integrating is bigger or smaller than the function you're comparing it to, then that may be able to tell you whether the function converges or the integral converges or diverges. So what would be a good function to compare this to? Well, typically, and this isn't like always the case, but many of the comparison theorem problems, you're going to be comparing to functions that are of the form 1 over x to a power. So we know that in general, the integral from 1 to infinity of 1 over x to the p dx, it converges if that exponent is greater than 1, and it diverges if that exponent is less than or equal to 1. And so in this case, if we were trying to see like what is the closest we can get to our integral, it would just be 1 over x, right? That's the thing that looks most like this type of integral. And so using the rule that I just wrote down, we know that the integral from 1 to infinity of 1 over x dx, we know that that diverges. So now we have to think, how does this function, this integrand, compare to 1 over x? So let's call 1 over x f of x. So f of x is 1 over x. And then g of x is going to be the function that we're working with here. So 1 over x minus e to the negative x. And I'm going to write this a different way that might make it a little bit easier to compare. What is e to the negative x? That's just 1 over e to the x, right? So we can rewrite this as 1 over x minus 1 over e to the x. So how do these two functions compare? Which one is bigger and which one is smaller when you're plugging in x values that are bigger than 1, right? And why do I say bigger than 1? Well, because we're looking at the integral from 1 to infinity. So we're only worried about positive x values. So if you aren't sure how to compare these two, go ahead and plug in some numbers. Like plug in x is equal to 1, x is equal to 2, x is equal to 3, and just see which one is bigger. Is this bigger or is this bigger? And what you should see is that this function ends up being bigger. So how can I tell that without plugging in numbers? Well, basically, the thing you need to understand about fractions is that the smaller the denominator of a fraction, the bigger the fraction, right? Like if you compare 2 over 5 versus 2 over 7, 2 over 5 is bigger, right? The denominator is smaller, so it's bigger. And so what's going on here, if we look at this denominator, it's just x. This one is x minus, and this is a positive number, right? 1 over e to the x, that's like, some small fraction. It's like 1 over e squared, 1 over e cubed. It's some kind of small fraction. And so what you're doing is you're taking an x value and you're subtracting some small value from it. And so the denominator of this function is smaller than the denominator of this function, and therefore, overall, the function with the smaller denominator is bigger. So again, I think it's a good idea to just kind of understand that how that works with fractions, when, that the fact that when the numerator, well, I didn't talk about that, but just talking about the denominator, when the denominator is smaller, the overall fraction is bigger. When the denominator is bigger, the overall fraction is smaller. But again, if you don't like doing that kind of comparison, you can literally just plug in numbers. Plug in 1, 2, 3, 4, 5. Convince yourself that one of these functions is bigger than the other. But yeah, so what we just decided is that g of x is a larger function than f of x for all values of x that are greater than or equal to 1. And so what does that tell us? Well, we know that the integral of f of x diverges. And so if we have a function that is bigger than a divergent function, well, that tells us that it must also diverge. So the integral from 1 to infinity of 1 over x minus e to the negative x dx also diverges. So that's our answer, and the comparison theorem is how we got there. All right, so next we have 1L, so another improper integral. So this one, again, pretty clear that it's improper because we have infinity as one of our bounds. So this is one where we're actually just going to evaluate it using limits. We're not going to use the comparison theorem. Again, as I mentioned in the last one, the comparison theorem really comes up in situations where you don't know how to find the antiderivative. This one we do. We've worked with functions that look like this before. So let's start by just rewriting this as a limit. So it's the limit as t approaches infinity of the integral from 0 to t of x times e to the negative x dx. So now we can just focus on evaluating this integral. And as I've mentioned in other cases, with improper integrals, especially if there's going to be, so if you're going to do something like substitution or integration by parts, if you have to really do any work to evaluate the integral, you usually want to make it into an indefinite integral and just focus on finding the antiderivative. Once you have the antiderivative, then you can bring it back and put the bounds in. So, don't think about kind of changing bounds and all that kind of stuff. I think that just makes it harder in a lot of these. And I think it's a lot easier if you just kind of get rid of the bounds, just focus on the antiderivative, and then you can bring it back to the bounds and the limit. So we're just going to focus on the improper integral x times e to the negative x dx. So what method would we want to use for an integral like this? Well, it's a product of two different functions that can't really be combined. And usually when that's your situation, you want to use integration by parts. And so in this case, we have one function, x, which becomes a lot simpler when you take its derivative. So that's what we want to set equal to u. And then the other function, e to the negative x, well, that one doesn't really change very much when you take its derivative or antiderivative, right? And so it's a good choice for dv because taking its antiderivative won't make things more complicated. Okay, so let's take the derivative of u is equal to x, so that would just be equal to 1 dx. And then the antiderivative of e to the negative x, well, that's negative e to the negative x. So you could do that with substitution, or I think this is one that it's kind of nice to be able to do in your head, right? So why is it negative e to the negative x? Well, if you take the derivative of e to the negative x, the chain rule brings out an extra negative sign. And so you need this negative sign to cancel out with that negative sign to bring you back to just positive e to the negative x. Okay, so let's go ahead and put these in. We have u times v, so that's going to be negative x e to the negative x. Minus the integral of du times v. So du is just 1, and so we have negative e to the negative x dx. And so let's simplify this a little bit. We can rewrite this as negative x e to the negative x plus the integral of e to the negative x dx. And then as we already talked about, the antiderivative of e to the negative x, well, that is negative e to the negative x. So we have negative x e to the negative x And then this will be plus negative e to the negative x. And then we have plus c, which we won't put in when we actually plug in our bounds, but for now, since we're doing an improper integral, I'll write plus c. Okay, so now let's go ahead and put that back into the context of this improper integral. So really what we're doing here is we're taking the limit as t approaches infinity. And now we have our antiderivative, so I'll write that down, negative x e to the negative x minus e to the negative x. And then we're evaluating that at t and at 0. So let's start by just plugging in our bounds, and then we'll worry about the limit. So the limit as t approaches infinity so if we plug in t, we get negative t e to the negative t minus e to the negative t. And then if we plug in 0, well, when you plug 0 into the first term, it's just 0, right? Because you have 0 times something else, so it's just 0. But then when you plug it into the second term, it's not 0, right? 0 or e to the 0 is 1, right? So this becomes minus 1, like that. Okay, so let's simplify that a little bit, and then we'll take our limit. So we have the limit as t approaches infinity of negative t e to the negative t minus e to the negative t, and then that becomes plus 1. So to evaluate this limit, let's kind of take these term by term. So let's start with this one. So let's separately kind of think about how would we find the limit as t approaches infinity of negative t times e to the negative t. So we can rewrite this as, instead of negative t e to the negative t, let's rewrite this as the limit as t approaches infinity of negative t over e to the t. Right, that's what the negative exponent means. So if you were to try to take the limit of the numerator and the denominator separately, they would both be infinity, right? I mean, we have a negative sign out front, but kind of forgetting about the negative sign for a second, the numerator goes to infinity, right? The limit as t approaches infinity of t is infinity, and then the denominator also goes to infinity. When you raise e to a really big number, you get a really big number. And so this is a kind of situation where you have to use something called L'Hopital's rule, right? So L'Hopital's rule can be used when you have a limit where the numerator and the denominator are either both going to infinity or both going to 0. So you sometimes call that infinity over infinity or 0 over 0. And so the way that L'Hopital's rule works is that it says that the limit actually stays the same if you just take the derivative of the numerator and the derivative of the denominator. So I'm going to bring this negative sign back into the numerator. It doesn't really matter, but I think that's kind of the clearest way to do it. So we're going to take the derivative, so I'm using prime notation to mean taking the derivative of the top and of the bottom. And so that would give us the limit as t approaches infinity of negative 1 in the numerator, and then the derivative of e to the t is still e to the t. Okay, so now what is the deal? What happens if you're taking the limit as t approaches infinity of negative 1 over e to the t? Well, now the numerator is just a fixed number and the denominator is getting bigger and bigger and bigger. And so anytime you have a situation like that where the numerator is one fixed number and the denominator is getting bigger and bigger, that is going to result in a limit of 0. So that deals with this first term. So now let's talk about the second term, which we'll see that we actually kind of already just talked about. So the next term is the limit as t approaches infinity of negative e to the negative t, which again can be rewritten as the limit as t approaches infinity of negative 1 over e to the t. And that's what we just did here, right? One step further, that's what we had at the end, right? We just talked about that. So the limit as t approaches infinity of negative 1 over e to the t is equal to 0 again. And so now we can return to our answer here, and we see that we get 0 plus 0 plus 1, and so our final answer is 1. So this improper integral converges. So I know this one was a lot of work, but again, I think when you're dealing with problems like this that are more complicated, try to kind of separate it out into steps, right? So the first step was rewriting this as an improper integral, but then it's really just becomes a integration by parts problem, right? So once you write it as an improper integral, just look at your integral and think about, how would I evaluate this? And you might have to use substitution, you might have to use integration by parts. Any of the methods that we've talked about are valid for actually evaluating the integral. So next up we have number 1n. So this again is a surprise improper integral. So why is this one an improper integral? Well, anytime you have a denominator in your integrand, there's a chance that it's improper. So you always want to think about what would make this denominator equal 0, and then check whether the values that make the denominator 0 fall within your bounds. So what values would make cosine equal to 0, right? Because cosine squared is 0 whenever cosine is 0. So think about, how do you find cosine of an angle? Well, cosine of an angle is the x-coordinate of the point that you draw on the unit circle corresponding to that angle. And so what would be an example of an angle where cosine is 0? Well, an angle of pi over 2, right? Because if you go to an angle of pi over 2, which is 90 degrees, then you would have coordinates of 0, 1. So cosine of pi over 2 is equal to 0. Another example of an angle where cosine is equal to 0 would be 3 pi over 2, right? 3 pi over 2 would give you the angle down here, 0, negative 1. So cosine of 3 pi over 2 also equals 0. And then you can also add 2 pi to any of those and get more examples of angles where cosine is equal to 0. But which of these is really relevant in this problem? It's pi over 2, right? And so this function is undefined at x is equal to pi over 2. And so that tells us that it is an improper integral. Okay, so we have to now rewrite this using limits. So this is going to be equal to the limit as t approaches pi over 2 of the integral from 0 to t. And actually we should add in here, it's specifically the limit as t approaches pi over 2 from the left, right? Because we're looking at values that are less than pi over 2 of 7 plus cosine squared of x over cosine squared of x dx. Okay, so now we can just focus on evaluating this integral. So like we've done on the other ones, let's kind of make this an improper integral so we can just really focus on the antiderivative, and then we'll put that back in when we're done. Although this one we'll see is actually, it's a lot easier than it looks to find the antiderivative, but I think it's just a good habit to get into. Okay, so how do we find the antiderivative of this? Well, it's actually a lot simpler than it looks. So remember that anytime you have a fraction with multiple terms in the numerator, you can always split that fraction up. So we can rewrite this as the integral of 7 over cosine squared of x plus cosine squared of x over cosine squared of x. And the second term here, now we can see, okay, that's going to simplify to 1. But the first term actually is pretty nice to work with as well, because what is another way of writing 1 over cosine squared? 1 over cosine squared is secant squared. So we can rewrite this as the integral of 7 secant squared of x plus 1. And so this is nice because the antiderivative of secant squared, that's just tangent of x. So we have a nice simple antiderivative. So we have 7 times tangent of x plus c. Okay, so now that we have our antiderivative, we can go ahead and put that back into our limit. So we're going to have the limit as t approaches pi over 2 from the left of 7 times tangent of x plus x, and we're evaluating this at t and at 0. I don't know how many parentheses I need, but I'll be safe and put more. Okay, so let's just plug in our values here. So we have, and actually I'll write it below. So we have the limit as t approaches pi over 2 from the left of 7 times tangent of t plus t. And then from that, we're subtracting 7 times tangent of 0 plus 0. Okay, so we're going to have to be evaluating tangent of some things here. So let's draw another unit circle. So remember that tangent of an angle is equal to sine over cosine, which is the same thing as the y coordinate over the x coordinate. So for example, here, tangent of 0, if you go to an angle of 0, sine of 0, actually I'll say cosine first. So cosine is the x coordinate, right? So that's 1. And sine is the y coordinate, which is 0. And so tangent of 0 is 0 because tangent is sine over cosine, 0 over 1 is 0. And then here we just have another 0, and so we're left with the limit as t approaches pi over 2 from the left of 7 times tangent of t plus t. Okay, so there's a couple of ways to figure out what the limit as t approaches pi over 2 from the left of 7 tangent of t plus t. So the plus t part isn't really going to affect much, right? So that's going to be just pi over 2. The limit as t approaches pi over 2 of t is pi over 2. So we want to focus on this and basically figure out whether this converges or diverges. So if this is infinity or negative infinity, then we don't need to worry about this plus t. We can just say, okay, it diverges. So how could you figure out what we get if you plug in numbers that are close to pi over 2? Well, you could just go into a calculator, plug in numbers that are close to pi over 2. I think another kind of nice way to think about it is to look on the unit circle or to think about the graph. So I'm just going to mention both of those. So on the unit circle, as I mentioned, tangent is always going to be your y coordinate over your x coordinate. So let's say that you're going to an angle that is like really close to pi over 2. So something like this. So if you take the y coordinate of that point, it's going to be pretty close to 1, right? Like the y coordinate of this point is almost 1. 1 would be if it was all the way up at pi over 2. And then the x coordinate is close to 0, right? The x coordinate is really, really small here. And so basically you're going to have 1 divided by, or something that's almost 1 divided by a very tiny number, and that's going to give you a really big result. So really the limit as t approaches pi over 2 from the left of 7 times tangent of t, that's equal to infinity. And so therefore the whole limit is equal to infinity. Another way to see this would be to look at the graph of tangent. So the graph of tangent has vertical asymptotes. It kind of repeats itself. So I'll just draw a couple of cycles of it. It does this over and over, and it has these vertical asymptotes that occur at different multiples of pi over 2. And so this first vertical asymptote occurs at pi over 2. And so if we see, what is happening to the outputs of this graph as our inputs approach pi over 2 from the left, we can see the graph goes up, right? And so the limit is infinity. And so this tells us that this function diverges, or this integral diverges. So next up we have number 3. So this is asking us to find the total distance traveled as well as the displacement of a particle. So I want to start by just reminding you about the difference between total distance traveled versus displacement. So the analogy that I like to give is, let's say that I am walking in a straight line, and let's say that first I walk in the forward direction, let's say 5 feet. So I walk 5 feet forward. Then I turn around and I walk the opposite direction 3 feet. And so if I asked you what is my displacement, the displacement would be the distance I am from my starting point. So this would be the displacement. It would be 2 feet. So what's going on with displacement is basically that you're allowing the travel in the negative direction to counteract the travel in the positive direction. So the 2 feet comes from 5 minus 3. Now, what about my total distance traveled? The total distance traveled does not care about which direction you're traveling, right? It's just adding up total, how far did you go? And so to find the total distance traveled, I would just say 5 feet plus 3 feet is 8 feet. So in this situation, we're asked to figure out both of these things. And that means that we basically need to figure out where is this particle moving forward or when is it moving forward and when is it moving backward. And so in order to do that, we want to know what the graph of the velocity function looks like, right? And so the velocity is given by v of t is equal to cosine of t. So let's start by just roughly sketching the graph of cosine. So hopefully you all know what the graph of cosine looks like, but it has a y-intercept at a height of 1, and then it goes through a full cycle in 2 pi, and so that means it's back to that same height at 2 pi, and then it goes down to its minimum halfway between, and then it goes through the x-axis halfway between those. So you can always just kind of use symmetry to help you to draw the graph of cosine. And then it repeats itself, right? It's a cyclic graph. And so if we're talking about 5 pi over 2, that's one of the times we're looking at, we have to keep going and draw it all the way up to 5 pi over 2. So if you had to kind of describe what's going on with how this particle is moving, well, it's going to be moving forward during the time periods when the velocity is positive. So whenever the velocity function, which is what we just graphed, lies above the t-axis, that means the velocity is positive. And if the velocity is positive, that means that it's traveling forward. Now, if we look at the places where the velocity lies under the t-axis, that would reflect when the particle is moving backwards, right? Because its velocity is negative. Okay, so if we're trying to find the displacement, remember displacement, it does allow negative travel to kind of counteract the positive travel. And so what's going to happen is when we go and integrate this, we're going to have some positive area up here, and we're going to have negative area down here, and we want those to counteract each other. And then the way that you allow positive and negative area to cancel out is just to do a normal integral. If you just do a normal integral, it will always count negative area as negative and positive area as positive. And so to answer part A, really we just want to take the integral from 0 to 5 pi over 2 of cosine of t dt, right? Because that's our velocity function. So displacement, you're just integrating your function because you want to allow that negative area to count as negative. So we could use symmetry and actually kind of figure this out without evaluating this entire integral, but let's just evaluate it. So, because I think that's a little bit faster. So the antiderivative of cosine would just be sine, right? So we have sine of t, and we're evaluating that at 5 pi over 2 and at 0. So we have sine of 5 pi over 2, and then we have sine of 0. And so if you were to go on the unit circle, and you were to go to an angle of 5 pi over 2, so 5 pi over 2 is like going all the way around and then coming back to an angle of pi over 2, so that's here. And then we have sine of 0 is here. So an angle of 0 has coordinates of 1, 0. An angle of 5 pi over 2 has coordinates of 0, 1. And so that tells us that sine of 5 pi over 2 is 1 and sine of 0 is 0. And so we get 1. And so our units are centimeters, right? It says in centimeters per second. So our answer here is 1 centimeter. So that means that basically this particle is 1 centimeter ahead of its starting point after 5 pi over 2 seconds. Okay, so next up we have this question asking us about the total distance traveled. And so to find the total distance traveled, we basically want to make sure that this part of the graph that lies below the t-axis is actually counted as positive instead of as negative. So the kind of technical way of writing that would be this. The integral from 0 to 5 pi over 2 of, let me write that a little better, of the absolute value of cosine of t, because basically we want to kind of force this graph to be positive, right? We want to look at it as if it was like this. But I don't think writing it like this is like the most useful thing, because there is no magical antiderivative rule for absolute value. I've seen a lot of people make mistakes trying to just kind of like pull the absolute value along the way with like your, just kind of take the antiderivative and slap some absolute value bars around it. It just doesn't work that way. So what I would do instead, it's fine to write it as an absolute value, but you really want to kind of split this up and think about what are the parts of the graph that are already okay as they are, and then what are the parts of the graph where I have to flip the sign. So the part of the graph from 0 to pi over 2, that's okay as it is, right? Because that part of the graph is already positive, and we want to count all the distance as positive in this part of the question. Now, the next part of the graph, the integral from pi over 2 to 3 pi over 2, that's where the graph is actually below the t-axis. And so what we need to do is add an additional or add a negative sign. And that might seem counterintuitive, but the reason that works is that the function is already negative there. So if we just contribute another negative sign, it will make the function positive. And so what we'll see is that when we do this integral, we'll actually get a positive result overall. If we did not have this negative sign, you would get a negative result when you did that integral. And then finally, we have this last little piece, which is the integral from 3 pi over 2 to 5 pi over 2 of cosine. And again, this one we don't need to flip because it's already positive. Now, one thing I want to point out is that there's a lot of symmetry in this. And I mentioned this in the last one, but I think now is really a good time to take advantage of it. Notice that if we just do the integral from 0 to pi over 2, the area we get for that part is going to be half of this area, right? And also half of the area in the middle, right? If we look at this flipped up so that it's positive, again, like it's just two of these pieces. So really all we have to do is find the integral from 0 to pi over 2 and then just kind of make sure we count up enough of those. That being said, if you did not notice that symmetry, it would be okay. You would get the right answer if you just kind of went through and evaluated all of this by hand. Okay, so let's do the integral from 0 to pi over 2 of cosine of t dt, and that's kind of our building block. So the antiderivative we mentioned already is sine of t, and so we want to evaluate that at pi over 2 and at 0. And so sine of pi over 2, that's the same as sine of 5 pi over 2, right? It's this 90-degree angle, and so that's equal to 1. Whereas sine of 0, we already know is just 0. And so this is 1 minus 0, and so that's 1. And so now, again, we can use this as kind of a building block. So we now know that this is an area of 1. And then we have another of those. We have like two more of those, right? We have another 1, another 1. We have another 1. We have another 1. And so altogether, that is going to be an area of 5. So we have 1 plus 1 plus 1 plus 1 plus 1 is equal to 5 centimeters. Again, if you're confused about this whole symmetry idea, you don't need to do it that way. You can just evaluate this. If you evaluate all of these integrals, you should get the exact same answer. All right, so next up we have this question asking us to write an integral representing the area of the infinite region bounded by y is equal to 1 over 1 plus x squared, x is equal to 0, and y is equal to 0. And then it says the region is unbounded on the right-hand side. So let's say that instead it didn't say the region is unbounded. You know, maybe it said and x is equal to 5. So what would that integral look like? Well, that would just be the integral from 0 to 5 of 1 over 1 plus x squared dx, right? Like when we very first learned about integrals, we learned that the integral represents the area bounded by the function and the x-axis. And that's exactly what we have here, right? We have a function, we have the x-axis, and then we have two bounds, x is equal to 1 and x is equal to 5. So that would be if we had an actual right boundary. But this says that it's an infinite region and it's unbounded on the right-hand side. And so that tells us that we actually want an infinity here. Okay, so now we can actually go ahead and evaluate this. So this would be the limit as t approaches infinity of the integral from 0 to t of 1 over 1 plus x squared dx. So what is our antiderivative in this case? Well, the antiderivative of 1 over 1 plus x squared, that is inverse tangent. So we have the limit as t approaches infinity of inverse tangent of x, and then we're evaluating that at t and at 0. So that's the limit as t approaches infinity of inverse tangent of t minus inverse tangent of 0. So inverse tangent of 0, that's just a number, right? We don't need to actually do a limit for that. You could plug that into a calculator, or really what this is asking, it's asking you, tangent of what angle is equal to 0. It's asking you, like, what does that angle theta need to be? And specifically for inverse tangent, we're looking at angles between -π/2 and π/2. And so that angle would be 0, right? The angle that gives you tangent equal to 0 is also an angle of 0. And so tangent of inverse tangent of 0 is 0, and we don't need to include that. So really, we're just trying to figure out what is the limit as t approaches infinity of inverse tangent of t. So again, as we've mentioned on some of these other problems, there's always a variety of ways to approach limits. One thing you can always do if you're in doubt is you can plug in numbers. You can plug in, t is equal to 100, t is equal to 1,000. In this case, that might not lead you to exactly the right answer, unfortunately. And that's because the right answer we'll see actually is in terms of pi. So how do I know that? Well, this is one that I think we went over in at least one video. So if you know what the graph of tangent looks like, you also know what the graph of inverse tangent looks like. So the graph of tangent basically has these kind of shapes that almost look like cubic graphs, and they repeat themselves, and they have vertical asymptotes at every odd multiple of π/2. So if you draw just one cycle of it, it would look like this. So this is the graph, again, not of inverse tangent, but of tangent. So this would be like f of t is equal to tangent of t. So why does that also tell you what the graph of inverse tangent looks like? Well, if you remember what the relationship is between a function and its inverse, the graphs are reflected over the line y is equal to x, or maybe a better way to think, or an easier way to think about it, is that you're basically switching your x and y coordinates. And so the graph of inverse tangent, instead of having these vertical asymptotes, it's going to have horizontal asymptotes. So it's going to have an asymptote at y is equal to π/2 and at y is equal to -π/2. And so instead of looking the way that this one does, it's going to look, and hopefully I'll draw this curved the right way. I think that's right. It's going to look something like this. So now if we're looking at this graph, so let me maybe name this. So let's call this g of t is equal to inverse tangent of t. So if we're looking at the limit as t approaches infinity, that's basically asking, as you go further out to the right, is there a specific value that this function is approaching? And it is, right? It's heading towards a height of π/2. So the limit as t approaches infinity of inverse tangent of t is equal to π/2. And so that is the area of this infinite region that we were describing. So I do think that this is an example that comes up fairly often. So I think this is a good limit to be aware of. And again, it's not like you have to memorize it. It's just being familiar with the general shapes of the graphs of tangent and then inverse tangent. Okay, so next up we have this arc length problem. So just to remind you, I'm giving you all of the formulas for all of these kind of new topics that we've discussed. I know that there's a lot of them. So you will have on the test formulas for arc length, and then all of the stuff involving parametric and polar equations. So the equation for arc length, if your function is given as a function of x, then the arc length is going to be the integral from a to b of the square root of 1 plus dy dx squared dx. So really what we need to do is we need to figure out what is the derivative of this function, dy dx, or we could call it f prime of x, and then just plug that into this integral. So dy dx in this case, or f prime of x, would be equal to, so we just need to take the derivative, right? So we bring down the 3, and so we have 3 over 12 times x squared, which we can simplify. And then the derivative of x to the negative 1 would be negative x to the negative 2. So this simplifies to be, so 3 over 12 is 1/4. And then negative x to the negative 2, we could also write that as minus 1 over x squared. Okay, so now we have to take this and actually square it, right? So that's one kind of additional step, is that in this formula, we don't just have dy dx, we have dy dx squared. So if we take this and square it, we have basically 1/4 x squared minus 1 over x squared times itself. Okay, so what happens when we multiply these together? Well, we do the first two terms, and that's 1 over 16 times x to the 4th. And then the middle terms are kind of nice because the x squareds cancel out, right? So if we do 1/4 x squared minus 1 over x, that's going to just give you minus 1/4. And then the same thing happens here. We have negative 1 over x squared times 1/4 x squared, and so that's just going to be another minus 1/4. And then we have the last two terms, and so that's going to be plus 1 over x to the 4th. And so this can be simplified into 1 over 16 x to the 4th minus 1/2 plus 1 over x to the 4th. Okay, so let's go ahead and put that into our integral. So we're going to have the integral, and we also need to look at our bounds, right? That was from 1 to 3 of the square root of 1 plus all this stuff that we just found. So 1 plus 1 over 16 x to the 4th minus 1/2 plus 1 over x to the 4th dx. So we can simplify this stuff inside the square root. And so this will now become, so we can combine the 1 and the negative 1/2. And so this is now going to be 1 over 16 x to the 4th plus 1/2 plus 1 over x to the 4th. Okay, so now comes kind of a tricky insight. So what you need to do now is recognize the fact that this new expression looks really, really similar to what we had before. So what we had before looked exactly the same, except for that we had a negative 1/2 instead of a positive 1/2. So basically, we know that if we have, so we know that 1 over 16 x to the 4th minus 1/2 plus 1 over x to the 4th, we know that that factors as 1/4 x squared minus 1 over x squared squared, right? That's how we found it. We took the derivative, which was this thing, and we squared it. And so now we have instead 1 over 16 x to the 4th plus 1/2 plus 1 over x to the 4th. And so how can that factor? Well, that's actually going to factor exactly the same, except for with a plus sign instead of with a negative sign, plus 1 over x squared squared. So how do I know that? It's basically just kind of a thing with factoring, right? So just to give a quick example that might be a little more familiar to you, let's say you have x squared minus 6x plus 9. Well, that factors as x minus 3 squared. If you take this exact, or the same expression and you just make a change on the middle term, just make it plus 6x, well, it's going to factor exactly the same, except for it will be x plus 3 instead of x minus 3. So my point is that the sign that you have in between the two terms in a binomial like this doesn't affect anything except for the middle term here. And so really when you have something that is just a binomial getting squared, you can just look at that middle term to figure out whether you have a plus or a minus. And so because these two expressions are identical except for that middle term, that tells us that they factor exactly the same except for the middle term switching to a plus instead of a minus. So kind of tricky, but we've seen a couple of examples like this in our video and probably on a worksheet. So that's something that you might want to be like on the lookout for. So why is that useful, by the way? Well, because now we have the square root of something squared, right? We can rewrite this as the square root of 1/4 x squared plus 1 over x squared squared. And so now we're taking the square root of something squared, and so the square and the square root will cancel out, and we're left with the integral from 1 to 3 of just 1/4 x squared plus 1 over x squared, which is actually going to be pretty straightforward to actually integrate, right? So now we're just going to have, let's rewrite it as the integral from 1 to 3 of 1/4 x squared plus x to the negative 2. So our antiderivative for the first part is going to be 1, so we still have 1/4, and then we have 1/3 x cubed. And then the antiderivative for x to the negative 2 is going to be minus x to the negative 1. Right? If you take the derivative of x to the negative 1, you get negative x to the negative 2, and so we need this extra negative sign to compensate. And we're going to be evaluating this at 3 and at 1. Okay, so this, let's just rewrite this as 1/12 times x cubed minus 1 over x. And again, we're evaluating this at 3 and at 1. So this is going to be 1/12 times, so 3 cubed is 27. And then we have minus 1 over 3. And then from that, we're subtracting just 1/12 and then minus 1. So now we have 27 over 12 minus 1 over 3 minus 1 over 12 plus 1. So let's combine our 12s and then we can make a common denominator. So now we have 26 over 12, which actually that can be reduced. So we can even make a smaller common denominator. Minus 1/3 plus 1. So this can now be written instead as 13 over 6. And then let's make these other ones into sixths as well. So 1/3, that's 2/6. And 1 is 6 over 6. And so altogether we have 13 minus 2 is 11 plus 12, 13 minus 2 is 11 plus 6 is 17. And so we're left with 17 over 6. I'm just double checking that that matches with yes, it does. Great. So again, kind of a tricky example, probably trickier than what I would give you on the test, but I think this is a pattern that comes up fairly often with arc length, so it's a good one to be aware of. Okay, so now we have a couple of differential equations. And so it says if no initial condition or point is given, write your answer in the most general form. In both of these cases, we do have an initial condition. So that means that we're going to be giving a particular solution. So let's start off with A. So usually when you're given your differential equation with a y prime, you usually want to rewrite it as dy dx because that will give us those pieces to work with. Okay, so our first goal with these types of differential equations is to get all of the things that have y in them on one side with the dy and all the things that have x in them on the side with dx. Now, one word of caution when you're doing that, when you're kind of getting things from one side to the other, the operations you want to use are multiplication and division. You don't want to add or subtract things from both sides. That's going to kind of lead you astray. Just because of how these are kind of set up, you want to use multiplication and division. So we can start by multiplying both sides by dx, and then also multiplying both sides by ln of y. So if we do that, we'll end up with dy, or let me write it this way, ln of y dy is equal to 7x squared y dx. So we've made some progress, right? We have the y's on one side, we have the x's mostly on this side, but notice we still have a y. And so we want to additionally divide both sides by y, and then we'll be good in terms of having the x's and y's separated out. Okay, so now that we have the x's and the y's separated out, now we can integrate each side. So on the left-hand side, we're doing the integral of ln of y over y. And on the right-hand side, we're doing the integral of 7x to the 6th. Oh, sorry, this should be a dy on the left-hand side. Okay, so focusing first on the left-hand side, this might initially look like kind of a complicated thing to integrate, but we can make a substitution. So why does a substitution work here? Well, if we were to let u equal to ln of y, the derivative of ln of y would be 1 over y, and we have a y in the denominator. So I'll write out the substitution, but it's going to be a very simple substitution that basically just kind of simplifies everything away, actually. So if we set u equal to ln of y, then du is 1 over y dy, right? And that's just like this whole thing. And so this whole integral is just going to become the integral of just u. And then I'll just leave this side as is because we'll do that side afterwards. And so what is the antiderivative of u? It would be u squared over 2. And we'll leave the plus c for the other side. But then we have to return to our y variable, right? We don't want u. And so what did u represent? It was ln of y. And so our antiderivative on the left-hand side is ln of y squared divided by 2. And then on the right-hand side, our antiderivative, so the antiderivative of 7 times x to the 6th, so we want to add 1 to our exponent and then multiply by the reciprocal. But notice that that would mean the new exponent is 7, and then 1/7 would cancel out with this 7. And so really the antiderivative is just x to the 7th plus c. And that makes sense, right? Because if you take the derivative of x to the 7th, you get 7x to the 6th, which is exactly what we had. Okay, so now our new goal is to solve for y. So at this point, we're done with the calculus. Now it's really all about isolating y. So we want to kind of peel back the layers, do everything that we can to get this y by itself. So first thing we can do to get closer to isolating y is to multiply both sides by 2. So that would give us ln of y squared is equal to 2x to the 7th. And then, we could write this as plus 2c, but really it's just, we can just still call it c if we want to, right? It's just a new constant. Technically, you could call this c1 and this c2, but it doesn't really matter because c just represents an arbitrary constant. Okay, so next step in isolating y would be to take the square root, right? We see that we have ln of y, so we're eventually going to want to do e raised to both powers, or to both sides. But we can't do that yet. We need to first get it just to be ln of y on its own. And in order to get that, we want to take the square root of both sides. So we end up with ln of y is equal to the square root of 2x to the 7th plus c. Okay, so now comes time to exponentiate. So we can do e to the ln of y is equal to e to the square root of 2x to the 7th plus c. And now e to the ln of y, well, that just simplifies to be just y, right? And in this case, there's no absolute value to worry about either because the ln basically came from the substitution and not from like the antiderivative, if that makes sense. So we're just left with y is equal to e to the square root of 2x to the 7th plus c. And so now the last thing that we need to do is figure out what is the value of c. And so the way that we can do that is to plug in the initial point that's given. So we're told that y of 0 is equal to e. And so that means that we want to plug in 0 for x and see what that gives us and set that result equal to e. So if we plug in 0 for x, we would get e to the square root of 0 plus c, right? If we plug in 0 for x, we just get 2 times 0 to the 7th, so 0. So that means that we have y of 0 is equal to e to the square root of c. And according to our question, that's supposed to equal e. So what number would c have to be in order to make this true? Well, c would have to be 1. Right? Does that make sense? If you wanted to, you could take ln of both sides to solve, but really I think the easiest way to do it is just to kind of think about it, right? Like, how do you raise e to a power and get e? Well, that power has to be 1. And so what would c have to be? C would have to be 1. And so we find that c is equal to 1. And so now we can go ahead and put that back into our function. So we had y is equal to this stuff. Now we can go ahead and put in the value of c that we just found. So we have 2x to the 7th plus 1. And that is our answer. Sorry, just flipping in my solutions to make sure I have everything up to speed. Yeah, that is correct. Okay, so next up we have another differential equation. So this one says y prime is equal to x times e to the x plus y squared x e to the x. So I'm going to start by, again, rewriting it as dy dx. Okay, so again, as I mentioned in the last one, when we're separating this, so when we're kind of moving things around, we only want to use multiplication and division. You don't want to be adding or subtracting. So even though it kind of looks like, oh, we have addition here, we should subtract something over. Maybe we should subtract over this stuff. That's really just going to get you stuck. So in order to make use of multiplication and division, we need to first start by factoring something out on the right-hand side. So what can we factor out from everything on the right-hand side? Well, they all have a common factor of x times e to the x. So if we factor that out, we're left with 1 plus y squared. So why is this useful? Well, now this will allow us to divide both sides by 1 plus y squared, and that will separate the x's and the y's without us having to use addition or subtraction. So I'm going to start by just multiplying both sides by dx before we do that. So now we have all of this times dx, and now we can divide both sides by 1 plus y squared. So we end up with dy over 1 plus y squared is equal to x times e to the x dx. Hopefully this won't get too cluttered with the other one next to it. I'll go like this. Okay, so now we can take the integral of both sides. So I'm going to rewrite this one as 1 over 1 plus y squared dy. And then we have the integral of x times e to the x dx. So on the left-hand side, this is inverse tangent, right? So the antiderivative here would be inverse tangent of y. And then on the right-hand side, we have to do a little bit more work. So we actually want to use integration by parts here, right? Because we have a product of two functions that can't really be combined with each other. So if we set u equal to x and dv equal to e to the x, that's going to work out because when you take the derivative of x, it just becomes 1. And then when you take the antiderivative of e to the x, it doesn't change, so it doesn't become any more complicated. So this is going to give us now u times v, so that's x times e to the x, minus the integral of du times v, so that's just e to the x dx. And so the integral of e to the x is just e to the x, and so we're left with x times e to the x minus e to the x plus c. So pretty quick integration by parts. So, okay, let's put that in on this right-hand side. We have x e to the x minus e to the x plus c. So now we just need to solve this equation for y. So how would we isolate y in this case? Well, we basically want to undo inverse tangent. So what would be the kind of function that undoes inverse tangent? Well, it would be tangent, right? So if inverse tangent of y is equal to all of this stuff, that would mean that y is equal to tangent of all this stuff. Okay, so now all we need to do is find the value of c, right? And so how are we going to find the value of c? Well, we want to go back to the fact that y of 0 is equal to 0. So we want to plug in 0 and see what happens. So if we plug in 0 for x, this first term is just going to be 0, right? So we have 0 minus, but then here we actually have 1, right? E to the 0 is 1. So this simplifies to tangent of -1 plus c. And then we know that this is supposed to be equal to 0. So we need to figure out, what would be a value of c that would make this work. Well, what angle, when you take tangent of it, do you get 0? Well, one example of an angle that would work would be an angle of 0, right? If you go to an angle of 0, that would have coordinates of 1 and 0. So tangent of 0 is 0. And so that tells us that this input here should be 0. I know it's confusing because there's a lot of zeros floating around, but this represents tangent. When I'm talking about this being equal to 0, that represents an angle, right? So this angle should be 0. And so that means that -1 plus c, that should be an angle of 0. And so now we can just solve this for c, and if we add 1 to both sides, we'll find out that c is equal to 1. And so now that we know that c is equal to 1, we can put that back into our answer here and say that y is equal to tangent of x e to the x minus e to the x plus 1. So next up, we have this question that is asking us to sketch a slope field, and we'll talk about this restriction in a moment. But basically, a slope field means a visual representation of what some solution curves to a differential equation might look like. So remember that anytime you have a differential equation, there are many different possible solutions, and those solutions are functions, right? Like just to give an example, we went over a couple right here. We found that the differential equation y prime is equal to x times e to the x plus y squared x e to the x, we found that that had a solution of this, right? Tangent of x e to the x minus e to the x plus c. And so this plus c means that you have a variety of different solutions, right? There are lots of different possible solutions, and really to pin one down, you need a little extra information. And so the way you can think of slope fields is basically this kind of like visual representation of what all of those different solutions could look like. And really the important part, the thing that I really want you to understand is that a differential equation is telling you a relationship between the slope, the x value, and the y value. And a slope field is really a way of kind of making that concrete. So what we want to do is we want to kind of take different points. So the points, 0, 0, 1, 0, 2, 0, all of these points, these 9 points, we want to figure out what, if there was a solution curve that went through those points, what would the slope of the solution curve be? And the way we can do this is basically by making a table. So we're going to make a table where we're going to take different points, different x and y values, and see what that would give us for y prime. And once we know what that gives us for y prime, that will allow us to kind of sketch a little representative of that slope. So let's start with the origin. So when x and y are both 0, according to this differential equation, y prime should be 0 minus 0, which is 0. And so what does that tell us? That means that if you have a solution curve that goes through 0, 0, it should have a slope of 0 at that point. And so that means you would have, like, it would be flattening out, right? It would have a horizontal tangent line at that point. Okay, so maybe let's move along the x-axis and let's do the point 1, 0. So if you had a point, a solution curve that went through the point 1, 0, we would have y prime is equal to 1 squared minus 0 squared, so 1 minus 0, which is 1. And so that means if you had a solution curve that went through that part of the graph, it would have a slope of 1 at that point. Okay, so next up we have 2, 0. So 2, 0. Now we have 2 squared. So again, we're just plugging into this equation. Y prime is equal to 2 squared minus 0 squared. So that's 4 minus 0, so that's 4. And so that means that if your solution curve went through the point 2, 0, it would have a very steep slope. It would have a slope of 4. Okay, so now we just keep going in the same fashion. So now let's maybe do all these values when y is equal to 1. So that would be the point 0, 1, and then 1, 1, and then 2, 1. So for 0, 1, that would be now 0 minus 1, so that's negative 1. And so that means that if your solution curve went through the point 0, 1, it should have a slope of negative 1. So that would look like this. And then we have 1, 1, so that would be 1 minus 1. So that would be 0. So if a solution curve went through this point, it would be kind of flattening out at this point. And then we have the point 2, 1. So that would be 2 squared is 4, minus 1 is 3. So it would have a steep slope, not as steep as the one down here, but still pretty steep. Probably steeper than what I'm drawing, but it's hard to draw really steep lines. Okay, last row. So now we have the points at a height of 2. So we can do 0, 2, 1, 2, and 2, 2. So 0, 2, that would be 0 squared minus 2 squared. So 0 minus 4 is negative 4. So again, this would have a really steep slope, but it would now be negative. So something like that. At 1, 2, we have 1 squared minus 2 squared. So 1 minus 4, which is negative 3. So again, really steep, not as steep, and negative this time. So something like that. And then finally, 2, 2 would be 2 squared minus 2 squared, so 4 minus 4, which is 0. And let me be consistent with my color here. So the curve would be flat. So just to be clear, this does not mean that any solution for this would somehow pass through all of these. It just means that if you had a curve that went through these points, it would kind of follow these slopes. So for example, you could have something that came in like this and then flattened out like this here, or something like that. And then, maybe did something else over here. But really the idea is just that, again, the thing I want you to understand is that the differential equation isn't just an equation to solve. It's also telling you something, right? It's telling you what the slope is as a function of the x and y coordinates. Okay, so this one, we're just going to do A because that was the one that was requested by more people. So this is asking us to eliminate the parameter to find a Cartesian equation for the following curves. And so basically what that means is finding a way to express this function not in terms of x of t and y of t, but just as y is a function of x. So we basically want to figure out a way to rewrite this relationship as y is equal to some function of x. That's our goal. So in a lot of these, the good approach to take is to basically solve one of them for t and then plug it into the other one. However, that's not really going to be a good approach here. And the reason for that is that solving this for t is kind of complicated, right? You would have to take ln of both sides and then plug the ln into the other one. It would work, and if you did it that way, it's totally fine. But I think it's a little easier to do this by just kind of thinking through it in kind of a clever way. So let's try to think, how could we build up e to the 8t using e to the 4t minus 5? So what's the relationship between e to the 4t and e to the 8t? Well, e to the 8t is equal to e to the 4t squared, right? And so if we can get rid of this 5, then we can just take that result and square it, and that can give us y. So there's a few different ways of writing this down. I'm kind of trying to think of what way makes the most sense. Let me write it like this. So if we were to rewrite this as e to the 4t is equal to x plus 5, that's another way of writing the same information, right? Just adding 5 to both sides. So now if we wanted to turn this into e to the 8t, we could just do that by squaring both sides of this equation, right? E to the 4t squared is equal to x plus 5 squared. And so e to the 4t squared, as we mentioned, that is the same thing as e to the 8t, because raising a power to a power is the same as multiplying those two powers. So e to the 8t is equal to x plus 5 squared. And so e to the 8t, well, that's y, right? And so now we can say that y is equal to x plus 5 squared. So I know this might not be super satisfying. You might be like, I don't get what like the method is. Again, if you really wanted to know just like what is a kind of method for this, you could take one of these and solve it for t. So for example, you could take this and take ln of both sides and say ln of y is equal to ln of e to the 8t. And then that would give you ln of y is equal to 8t. And then divide both sides by 8. And then take this value of t and take this whole thing and plug it in here. And you would get the right answer. It would work. It would give you actually x as a function of y, which is a little funny, but then you could move things around and get y as a function of x. But I just don't think that's the easiest way to do it. So I think another kind of good thing to keep in mind is just like looking for a relationship between these two expressions and thinking like, how can I manipulate one of these to make it into the other? And in this case, if you notice that, okay, like these are kind of similar, you can just kind of unpeel the steps, right? Say, okay, first I need to add 5 to both sides, then I can square it, and all of a sudden here I am with the y I was looking for in terms of x. Okay, so next up we have a parametric equation. So we're asked to sketch the curve defined by these parametric equations. So we want to start by making a table. And basically, we're going to run through different values of t, and this specifically tells us that we're just looking at t being between negative and positive 2. So negative 2, negative 1, 0, 1, and 2 should be enough for us. And then we're going to use these two equations to figure out what x and y are. And then we're going to kind of forget about the t values and just plot our points with x and y coordinates the way we normally do. Okay, so for example, when t is negative 2, if we plug that into this equation for x, we'd have 2 times negative 2 minus 4. And so 2 times negative 2 is negative 4, minus 4 is negative 8. And then if we plug in negative 2 to this one, we'd have 3 plus negative 2 squared. So that is 3 plus 4, so that's 7. And so that tells us that our graph is going to contain the point negative 8, 7. So I'm going to go ahead and plot that. Okay, similarly here, we now have plugging in t is equal to negative 1. So that's negative 2 minus 4, so that's negative 6. And then plug it into this one, and we get 3 plus 1, which is 4. And so now we have the point negative 6, 4. Okay, now plugging in 0, we have 2t minus 4, that's negative 4. Plugging in 0 to the second one, we get 3. So now we have the point negative 4, 3. Then we plug in 1, we have 2 minus 4, so that's negative 2. And then we plug it into the other one, we get 4, so we have negative 2, 4. And then finally we have t is equal to 2, so that's 2 times 2 minus 4, so that's 0. And then plugging t is equal to 0 into the second one, we get 3. So we have 0, 3. Wait, sorry, I did that wrong. It's not 0, 3, it's, so y is equal to 3 plus t squared, so that's 3 plus 2 squared, so 7. Sorry, I got a little, was focused on the x value. So we basically have this shape. We have, it's a parabola, and if you were to eliminate the parameter, you could get the equation for that parabola. And then the other thing we want to add in are some arrows. So that's kind of the value of parametric equations, is that they can be used to represent kind of like the motion of a particle or some object. So because we know that we are starting at negative 2 and going to positive 2, that kind of gives us a direction for this object. So we started at this point up here, right? We ended at this point here. And so it tells us that our object is traveling in this direction. Okay, so in this problem, we are asked to find the slope of the line tangent to a curve defined by parametric equations. at a particular value of t. And so really this is asking us to find dy dx at t is equal to 5 pi. And so this is another formula that will be on your formula sheet anytime you're dealing with parametric equations. This actually, I think of all of the different equations to know, this one is actually not too bad because kind of, you can just think of it as like the t's are canceling out. So to find dy dx, you're going to find dy dt and divide that by dx dt. So dy dt, so really this part is now just kind of doing regular derivatives. So dy dt, we're taking the derivative of t times sine of t, so we need to use the product rule. So product rule says take the derivative of the first thing first, so t derivative of that is 1. So we have 1 times sine of t. And then to that we add the derivative of the second thing times the first thing. So it's just going to be t times derivative of sine is cosine. So this simplifies to just sine of t plus t cosine of t. And then dx dt, so now we're taking the derivative of t times cosine of t. Same idea, we use the product rule, so we have 1 times cosine of t. And then second part of the product rule, we're taking the derivative of cosine, so it's negative sine, and we're multiplying it with just t. So this can be written as cosine of t minus t sine of t. And so now dy dx, we're just going to write it down as dy dt over dx dt. So dy dx is going to equal sine of t plus t cosine of t divided by cosine of t minus t sine of t. All right, so now we can go ahead and plug in 5 pi. So we're going to plug 5 pi in for all of the occurrences of t. So now we have cosine of 5 pi minus 5 pi sine of 5 pi. And so now we just need to know what sine and cosine of 5 pi are. So if we draw a little unit circle, 5 pi is basically like going all the way around 2 pi and then going an extra pi. So 5 pi lands you here on the unit circle. And so the coordinates of this point are -1 and 0. And so that tells us that sine of 5 pi is 0 and cosine of 5 pi is -1. So here we have -1 minus 5 pi times 0. So altogether, this is going to give us, in the numerator, -5 pi, and in the denominator, -1. And so these are going to cancel out and give us just 5 pi. So that is the slope of our tangent line at 5 pi. So it kind of works out in a funny way. The slope is the same as the actual y value, or sorry, the t value. Okay, this is similar to the last one. So in this question, we're kind of working backwards. So instead of finding the slope of a tangent line, we're finding the points where the function has a horizontal tangent line. And so basically we're trying to figure out for which values of t, and then that will help us figure out what values of x and y satisfy dy dx is equal to 0. Okay, so first thing we need to know is how do we find dy dx? So this is on your formula sheet. It's going to be dy dt over dx dt. So dy dt, we're taking the derivative of this function with respect to t. So that's just going to be 3t squared minus 6t. And then dx dt, we're taking the derivative of this function. And so that is going to be 3t squared minus 3. So everything is divisible by 3 in this, this derivative, right? So we can just divide everything by 3. And so that will leave us with t squared minus 2t over t squared minus 1. So now we want to set this equal to 0, right? Because we want to figure out where is the tangent line horizontal. The tangent line is horizontal when the derivative is equal to 0. So when is a fraction going to be equal to 0? It's going to be equal to 0 when the numerator is equal to 0, as long as the denominator is not also equal to 0. So we basically just want to set the numerator equal to 0, and then at the end we just want to double check that whatever values of t we find do not also make the denominator 0. So from here it's just factoring. We can factor out a t, and we're left with t minus 2. And so this tells us that either t is equal to 0 or t is equal to 2. And notice that neither of those values make the denominator 0, so we're good. We have 0 over something else, which is equal to 0. So we're almost done. The last thing we need to do is just plug those values in to figure out what those actual points are. So when t is equal to 0, we have x is equal to, so just looking at my sheet here so I don't have to write it or scroll back up. So we have x is equal to, so it's t cubed, so it's going to be 0 cubed minus 3 times 0 plus 2. And then y is equal to t cubed minus 3t squared, so 0 cubed minus 3 times 0 squared plus 2. So for the first one, we get 2. For the second one, we get 2. And so that tells us that one of the points, x, y, where this graph has a horizontal tangent line is at the point 2, 2. And then the other thing we had was t is equal to 2. So again, we just want to plug that in to figure out what does that actually tell us for x and y. So we have 2 cubed minus 3 times 2 plus 2. And then for the y coordinate, we have 2 cubed minus 3 times 2 squared plus 2. So for the first one, we have 8 minus 6 plus 2. So that's going to be 4. And then for the second one, we have 8 minus 12 plus 2. And so that's negative 2. And so that gives us the point 4, negative 2. So these are the 2 points where the function has a horizontal tangent line. All right, last question is asking us to find the area of one petal of the curve defined by r is equal to cosine of 3 theta. So I wouldn't expect you to kind of like have this graph memorized or anything like that. I would probably give you the graph or kind of walk you through how to sketch it yourself if I was going to ask you to find this area. The other thing or one thing we need to know in order to answer this, so, we're finding the area of one petal. We could kind of choose which petal we want. Usually it's going to be easiest to pick the one that's kind of like first, like closest to 0. It might seem clear to you that this petal kind of occurs between negative pi over 6 and pi over 6. It's not always as clear as it seems, what the first and the last angle are. So if that's something that's been confusing you at all, that sometimes the angles where it starts and stops are not exactly what you expect, I wouldn't worry about that too much. Like on the test, I'll make sure that the examples I'm giving you, it'll be pretty clear where you should start and stop integrating. In this case, it is negative pi over 6 and pi over 6. But again, you can't always just assume that based on what the graph looks like. It really has to do with if you were to actually go and plug in t is equal to negative, or theta is equal to negative pi over 6 and theta is equal to pi over 6 and all those values between, does that actually give you this portion of the graph? And in this case, it does. But there are some times where things don't line up exactly the way you would expect. But yeah, so basically in this case, what we want to do is we want to use the formula that is the area of a region bounded by a polar curve. And so that formula is going to be the integral from a to b, and so a and b here represent angles, of 1/2 r squared d theta. And so r is expressed as a function of theta, right? And so as I mentioned, in this case, our bounds are going to be negative pi over 6 and pi over 6. Again, it will be clear on the test what your bounds should be. And then for r, we're going to go ahead and put in cosine of 3 theta. So we're going to end up with cosine squared of 3 theta d theta. So we can take this 1/2 outside, and then there's something else we can do that will make this a little nicer, is we can, instead of going from negative pi over 6 to positive pi over 6, we can just go from 0 to pi over 6 and then double our result. And so that's basically because this shape is symmetric. So it kind of boils down to, instead of doing the whole petal, just doing like the top half of it. And then another way you can think about why you can do that is just by looking at this integral. So cosine is an even function, and anytime you have an even function, it's symmetric about the y-axis. And so cosine is even, cosine of 3 theta is still even, cosine squared of 3 theta is still even. Because it hasn't been shifted left or right, it still has that symmetry about the y-axis. If you didn't do that, if you didn't recognize that you could do that, that's fine. Let me actually just write out kind of this in 2 steps so that I'm not doing too much at once. So I'm going to start by pulling out that 1/2. And now, as I mentioned, we can do this instead from 0 to pi over 6, and then pull out a 2. And so we'll have 1/2 times 2, and those are going to cancel out, and just, we won't have a coefficient out front anymore. But like I said, if you did not recognize that, you would be fine. You would get the same answer. It just makes our life a little easier to only have to plug in 0 as our lower bound. Okay, let me just simplify this one more time. Just give us a nice clean integral to work with. Okay, so this is where we have to now use a trig identity, right? So we know there's like different rules that we can use for different trig integrals, but those usually will be when we have like odd powers of either sine and cosine. When we have even powers, we have to use these other identities. So the identity that we use for situations like this would be that cosine squared of x is equal to 1/2 times 1 plus cosine of 2x. And so the important thing to notice here is that whatever your input is over here, your input here is going to be twice it. And so in this case, because our input of our original function is 3 theta, the input in the identity is going to be 6 theta. It's going to be twice as much. So we're going to have the integral from 0 to pi over 6 of 1/2 times 1 plus cosine of 6 theta d theta. And so one last time, we can pull out this constant. And so we're left with 1 plus cosine of 6 theta d theta. Okay, so now we can take our antiderivative. So the antiderivative of 1, that would just be theta. So we have 1/2 times theta plus, so the antiderivative of cosine of 6 theta, you could do a substitution, but this is one of those kind of like substitutions in your head that I think are kind of easier to do in your head. So it's going to be sine of 6 theta over 6, because you need this division by 6 to compensate for the chain rule that would happen when taking the derivative of sine of 6 theta. Okay, so we have this, and then we're going to be evaluating this at 0 and at pi over 6. So this is going to give us 1/2 times, so let's plug in pi over 6, so that's pi over 6 plus sine of, so 6 times pi over 6 is just going to be pi over 6. And then from that, we're going to subtract 0 plus sine of 0 over 0, or sorry, over 6. Okay, so we have to, again, draw our unit circle. Just quickly remind ourselves what sine of 0 and sine of pi are. So 0 would be here. Again, sine is the y-coordinate, so sine of 0 is just 0. And then pi would be over here, coordinates of -1 and 0, but that's the same y-coordinate, right? So sine of pi is actually also 0. And so we're left with 1/2 times pi over 6, and then we have plus 0 minus another 0. And so at the end of the day, we're just left with pi over 12 as our area. All right, so that is it for this video. If you have other questions, definitely don't hesitate to send me an email and ask me, or stop by office hours. And good luck with your studying.